It's exciting to be here. Thanks for coming. We're going to talk about coroutines in Kotlin. So my name is Venkat Subramaniam. We're going to talk about a little bit about why should we really care about coroutines. We'll talk about parallel versus running as a coroutine. And then we will jump in and talk about how we can actually use coroutines in Kotlin. Best time to ask questions is anytime. If you have any questions or comments, fire away the questions. I'll be delighted to hear from you, and then we'll discuss about those things along the way. So let's get started. Well, one of the things that we have seen quite predominantly in Java is we focus on parallelism mostly in Java, if you really think about it. So we do a lot of coding in Java where we use sequential versus parallel. But I think the world is moving more and more towards asynchronous programming more than parallel processing in the long run. And Java is getting towards that. We are seeing changes in this area. I'm really excited about what's happening in the field of Java itself, like in terms of Project Loom and Fibers and so on. So a lot of exciting times ahead of us. But Kotlin is a bit ahead of time itself. It's providing some really cool things, and that's what I want to focus on today, talk about some of these things. Well, I want to think about the word non-blocking. So what does non-blocking really mean? Well, here's an example. I could say, hey, what's the time right now? And I could wait for you to tell me what the time is. And then when you tell me what the time is, I could say, what's the weather like? And you could tell me how cold the weather is. Or I could simply say, hey, what's the time? What's the weather? And I could go about doing my things, and you could tell me when you know the time, you could tell me when you know the weather. I don't have to block and wait on it. That's basically the idea, is we can get a better throughput by doing non-blocking calls. This is especially true in the world of microservices we live in. We really want to rely upon a lot of non-blocking calls, and that uses a better throughput. Let's talk a little bit about parallelism just to compare and contrast a little bit so we can appreciate this a little bit better. So let's jump over to Java for just a few minutes. Bear with me here. So what I want to do here is to start with a list of, let's say, integer values. And I'm going to say numbers is equal to. And let's go ahead and say, in this case, what I want to do is list of. And let's go ahead and create a list of numbers, let's say 1 to 10. But what I want to do is, let's keep it extremely simple. I'm going to say numbers.stream. But I want to do a map operation on it. And then what I'm going to do here is, given an element, I want to transform the element. And then when I'm done with it, I'm going to simply print it. So for each, well, actually, let's go ahead and do a reduce on it. So we'll say reduce, and we will simply say integer, and we will call a sum method on it to total it up. When we are done with it, we'll just simply output it. So very simple code. What does the transform method really do? I'm going to keep it extremely simple so we don't have to spend too much effort thinking about it. So here's the transform method, which takes a number, and all it's going to do right now is simply return for us, let's say return number times 1. So as trivial as you could imagine, that's what it's doing. You can see the result is 55 right there when I run it. But what if I were to put a little try block right here? And within this, I'm going to put a sleep of, let's say, 1 second. And I'm going to now say over here, execute the code. And you know the answer for this. When I run the code, it's going to take about 10 seconds to run, as you would expect. You can see the beach ball right there because it's taking the time to run. And when it's finished, of course, it's going to give us the result. So that was a 10-second. Assume this is some computation that's going to take some delay. Now the question is, what is really good about streams? I want you to think about this for a minute. Think about the past for a minute. So what was the past, the scary past? What was it? The scary past was the structure of parallel code. Code was different from the structure of sequential code, right? So if you really think about it, if you were programming back in time in Java, and if you wrote a for loop, and you had everything working, and when you have everything working, somebody comes to you and says, let's make this faster, let's make it parallel, and let's introduce threads. At that point, the only good response is to start laughing, isn't it? Because the choices are to laugh or to cry. You better laugh at it. Because it's really hard to make this change. It is absolutely troublesome. What does the code really do? The sequential, beautiful code turns into a monster in front of you, and everything goes south after that. But the present, what can we do really beautifully? The structure of parallel code is the same as the structure of sequential code. This is one of the beautiful things we have realized in Java 8. So the structure of parallel code is the same as the structure of sequential code. How so? When I run this code, you saw how this code is taking 10 seconds to run, and you can see it's still trying to run. I ran it about a few seconds ago, and you can see the beach ball, and eventually it comes back with the result. But you know you don't have to really do this. All you do is simply go here and say parallel stream, and then you can run this code right away, and right after a second delay, you get the response, not after 10 seconds. But the beauty is the code structure was exactly the same. The code can be written sequentially, it can be debugged, it can be tested, it can be resent with, and then you can turn off a master switch and you can get parallel out of it, how easy it is. So this is something we appreciate really a lot in Java. Streams give us the ability. But also notice that code is a functional style code, so maybe I should make a small change here. The structure of parallel code is the same as the structure of sequential functional code, right? Because the code is not imperative, the code is functional style code. Well, leave the thought aside. We'll come back to this and talk a bit more about this in a few minutes. But why not simply be happy about it? Why not just stick to it? Hey, this is great, let's just do this. Functional style code is awesome. How many of you love functional programming? Yeah, that's me, I'm in the camp too. I love ice cream too, but I can't have it for everything I do, right? So there are places for it. So what is really good about functional programming? I love it because it removes accidental complexity. It makes the code easier to read, easier to understand, easier to work with. It makes it fun to write code. It removes all that accidental complexity. But one area where, two areas where functional programming really fails is if your code has impurity in it, it doesn't work really well. And if your code is going to deal with exceptions, but not just exceptions, but if you have to deal with multiple levels of exception, how do you write functional style code to deal with it? The short answer is, it's not fun. And every one of us who loves functional programming will begin to hate it at that point. So there is a really beautiful time when this makes really good sense, and all of a sudden, it's not as good. And we're not able to deal with impurity really well. We're not able to deal with exception really well. On the other hand, what about imperative style of programming? It is really good at what functional is not good at. And it's really bad with what functional is good at. So maybe when functional is really a good choice, we can use it. And if functional is not a good choice, maybe we can step back and use imperative style. And that's exactly what we're going to look at here. And exception handling is complete mess. What can we do about it? I want you to put that thought away. We'll come back to this again and talk about it again. But now let's talk about coroutines. So what are really coroutines? Coroutines are asynchronous. So what is asynchrony? Asynchrony is where you can set something run. Here's the way to think about it. Imagine I want to have a party. Well, of course, you cannot have a party without pizza and drink. So what can I do? I can ask one of my friends to go get pizza, and we all could wait. When the pizza arrives, I can ask another friend of mine to go get drink, and we can wait for it. But no party ever goes that way. Nobody would come to your party if you do it this way, right? We want to have some fun in the party. So what do? You tell one of your buddies, go get pizza, another buddy to go get the drink, and you get the party started, turn on the music. Now, pizza arrives or the drink arrives. Why would you wait for the other? When the drink arrives, you start drinking. When the pizza arrives, you start eating. That's what real parties do. That's kind of asynchrony. As things kind of move around and arrive, you start doing things rather than waiting for the whole thing. Parallel is usually let things go and you synchronize and move forward. Asynchrony is you let things go, and as they kind of happen, you keep moving forward, doing stuff. You don't wait for things to synchronize at that point. Now, in that point of view, let's talk about synchronous versus asynchronous just a little bit to understand how that works. So here I'm in Kotlin. How can you tell I'm in Kotlin? Because you start with fun, because Kotlin wants you to remember having fun every single time. So you say fun task 1, that's my very first function I'm going to write. And what am I going to do within this function? I'm going to print enter, let's call it as enter task 1. So I'm entering the task 1, and then I'm going to print out exit task 1. I know this is a really trivial example, but nevertheless works really great. Now I have a task 2 here, and I'm going to enter task 2 and exit task 2 as well. But what I want to do really here is to do these two tasks. How am I going to really do it? So I'm going to say run blocking. This is simply telling my thread, hang on, don't run away until this task is finished. I'm going to say task 1 over here. I'm going to say task 2. And then I'm going to simply say started, and I'm going to say that I started these 2 tasks. So such a simple code, isn't it? Nothing really complicated, nothing really difficult to see, fairly a simple code for us to work with. So given this, of course, what I want to do here is to fire it up and run this code. And what is the code going to really do for us? It doesn't know what run blocking is. Comes our first thing here. So import Kotlin X, which is an extension library for Kotlin, a coroutine, and then I'm going to bring in this case, of course, the library that we are interested in using. I want you to take a close look at the sequence of the output in this code. You have enter task 1, enter task 2, enter task 1, 2, enter exit task 2, and then started. Hey, we all know what's happening here. It's pretty darn sequential. That's how you expect things to work. You did the first work, it finished. Second work, it finished. And then it printed. The result started right after that. That is a synchronous execution, as you can see right there. But what about asynchrony? Asynchrony is where you can let things run off and you can keep moving forward. And that is something you can do quite effectively, for example. So as an example, what I'm going to do here is, I will go back to this code, and I'm going to simply say over here, let's go ahead and say launch, and I'm going to launch a request to run those 2 things asynchronously. So all I did was I called a launch, and I'm saying, go do this for me while I go do other things. So notice I launched the thread, and I'm going to go ahead and call started. If you remember the last time we ran the code, it said task 1 first, task 2 first, and then it said started. Now when I run the code this time around, notice what the output tells us. It says started first. Then it said task 1, and then it said task 2. That's a proof already that this is asynchronous, isn't it? Because we didn't wait for the launch to finish. We set off the launch to go, and we printed started, and the launch kicked in and executed it. So that is an example of asynchrony right in there, that the code block for the launch is running asynchronously while the main is finishing up the started. Of course, the question is, what kind of thread are we running it in? Don't worry about that right now. We'll talk about this a little bit later. But moving a little forward, I want you to think about concurrency instead of parallel. So what does concurrency really mean? How many of you here can walk and talk at the same time? Yeah, that's awesome, isn't it? Some of us can do that, right? We can walk and we can talk at the same time. But how many of you can eat and speak on the phone at the same time? Okay, one person. There's always that one person. But the rest of us don't do this. A, because it's not very civil, right? But secondly, it's really hard to speak while you're munching something, right? That doesn't go really well. So what do you normally do? You take a bite, you eat, and you have something to say, you swallow, hopefully, and you say something, I agree, and then you take another bite and you eat it. Notice your mouth is either speaking or you're munching. But given a timeline, you are eating your food and you're talking on the phone, that's concurrency. Concurrency is where 2 things are happening at the same time, but you're not really doing 2 things at exactly the same moment. You're either munching your food or you're speaking to say something on the phone, but you're not doing the same thing at the same time. That's an example of concurrency where you can interleave these things. That's the word to think about, interleaving. Hey, what about interleaving here? I want you to one more time watch this very carefully. Let's go ahead and run this code real quick. And when I run the code, you can see what the order was. You know what? Let's make this a little easier. Here you go. And you can see the order in which it ran. It said started, enter task 1, exit task 1, enter task 2, exit task 2. I want to save this away for us to see this. So let me just grab this away so we can compare with this in just a few minutes. That's our current execution of code. I'll leave that on the side. But what I want to do now, though, is I want to really interleave. So what am I going to do? Notice it's exactly the same code. I didn't change it. But I'm going to go here to the code and say yield right here. And I'm going to go to the same code here and call yield. Pause right there for a minute. Let's understand what we are doing. Some of you may have been used to the command called nice on Unix. Remember that? What does nice do? Nice actually is what the true definition of nice is. You give opportunity for somebody else to do their work. Yield is kind of like nice. So this task 1 says, I enter task 1, but I'm going to quietly yield. I'm going to give an opportunity for this other task to run if there is another task. Task 2 comes along and says, I'm going to yield as well. They're a bunch of very nice people, right? So they both yield, and so they can interleave with each other. Wouldn't that be so cool if that can happen? Let's see if that actually does. So when I go back and look at the output of the code, what's going to happen? If I look at the output of the code, oh darn it, that didn't quite work. The reason why it didn't work is you are telling this particular code to suspend its operation and yield to another thread. Now step back for a minute. This is one place where I really have an opinion about language designs. I want the languages to make things very easy for us, but not to the extent where it's so easy you don't even know what just happened. So I want language designers to think of not seamlessness, but I want it to be almost seamless. So what does almost seamless mean? It is so seamless you don't have to do much except for one little marking that gives you a visual cue that something else is happening. So what do we do here? You're telling the compiler, hey, I'm aware of what's going to happen here. This function, when called, potentially may suspend. So what do? You say suspend, and you say this. By the way, just as a side note, that breaks my heart. Suspend fun. Who wants to suspend fun anyways, right? But anyway, play of words. So suspend function right there, you're suspending it. And then of course you're going to say suspend over here as well. And I'm going to say that these are suspendable functions. That's what you're saying here. Now what's going to happen when I run the code? When I run the code, the output is very different. I want you to compare the two output right here. You see the remarkable difference, isn't it? On that side over there is the task 1 finishing and task 2 finishing. On this side though, we enter task 1, and what's going to happen in this case? Well, actually, is it the same? Yeah, well, okay. Look at how confident I was, right? Okay, so what's going to happen at this point, when I want to run this, I want that to run in the opposite direction and provide us the result after all. So this should actually enter task 2 at this point and run through right in here within the main function. So potentially this can yield the code and give us an opportunity for us to run the other task and come back and execute it. Let's see if it actually wants to do that. Okay, so let's go ahead and put a little delay here just to see if that's going to cause any change at all. This is the beauty of demos, right? It works until it doesn't. So let's try this one more time. So it still doesn't want to do it. Anyway, just believe me. So in this case, you can actually have this delay it and run through it and ask you to run. Let's try one more thing just for the sake of it. Let's go ahead and put it in a completely different thread. So I'm going to say global scope.launch. That way it actually runs in a completely different thread, and maybe that will give us a little bit of a output here. So if I run this again, let's see what it's going to do. Okay, it still doesn't want to do it. Okay, let's move forward. We'll worry about this later. So what I was hoping to show you here is it enters the task 1, but of course, it's going to yield and go ahead to task 2 at this point, execute it, and then of course, come back and finish up that particular task because we call the yield. That's what I would expect it to work. So when it comes to this, think about coroutines, if you will, from the point of view of how this is going to actually run for us. I'm going to try to steal a little code here and see, maybe I'm making absolutely a stupid mistake, and maybe we can recover from that. So give me opportunity to do that 1 second, and then we will move forward right after that. So what I want to do here is to show you the asynchrony, and I'm really doing the concurrency at this point. So let's see if I'm able to really do that here with this example. So let me try this one last effort to give you this example. So notice here that I came in. I don't think it's anything different in this code than I did before. And then of course, I'm going to invoke the task and ready to run. That's what I'm really trying to do. Let's see if that's any different at all. Yeah, so seems like you can see, is it different now? Okay, all right. So I don't know why it was different, but it is. We'll take it. So in this case, you can see how the enter task 1 and then it entered task 2, but you can see that it came back to exit after a later time. this is exactly what I wanted to show you in terms of how this yield is doing the job when you suspend the function and run it. Oh, actually, I put 2 different launch here. That's why. Okay, fair enough. So that's basically what I did. I launched them on both of those. You know what is really funny about this, though? You may be curious what thread is running this whole thing. Just to illustrate the point about it, let's do one more thing. Let's come in here and quickly say thread.currentThread, so we can see what thread is running right here. So we'll say thread, even though I call launch 2 times, which is the point I wanted to really make. And then I'm going to put the current thread here also, and the current thread here also. So we can just take a quick glimpse on what the thread is running this. But did you notice all that is in the main thread, which is the point I wanted to make? This is the interleaving. Me speaking on, for a minute, taking a bite, and speaking on the phone. It's still me, but I'm interleaving between these 2 tasks in the main. We didn't create new threads at this point. Literally, main was interleaving between these 2 calls, and that's exactly what I wanted to show in this example. So this shows us how the interleaving happens. That's great. So I want you to think about this as coroutines. So what does coroutine really mean in this context? So in terms of the coroutines, we'll come back to this in just a minute. Let's go ahead and take a slightly different example. I want to say val sequence over here is equal to sequence, and I'm going to say for, let's say in this case, a number in sequence. And I'm going to simply print out, I'll say in the loop, and I'll print the number out. Before I write more code, let's talk about what is happening here. If you look at this, this is kind of like a lambda, isn't it? What is a lambda? Lambda is an anonymous function. Well, typically what do? When you have a function, you enter the function and then you exit the function. But if you really think about it, this is one of the reasons I get excited about programming languages is, sometimes you are used to one thing and suddenly a language comes and changes the way you think about it. For example, if you're programming in a language where you have a parameter list, we typically used one parameter list to every function. And then suddenly you come across languages like Scala where you can actually have multiple parameter list. And that kind of shakes your faith in everything. It's like, whoa, I could actually have multiple parameter list. Similarly, in the case of coroutines, coroutines have been around for a very long time. They've been around for, 40, 50 years now. But what is a coroutine? A coroutine can have any number of entry points and exit points. So think about it this way. Imagine you have a very long freeway, and you're driving on the freeway. You could exit the freeway anytime you want to, because maybe there was a traffic jam or an accident, and you can re-enter the freeway again. So if it's a very long stretch of a freeway that runs for 50 kilometers, nobody says you have to be on the freeway entirely. You could exit and enter any number of times. And so much like this, what if we can enter this function and exit this function multiple times? So notice what I'm going to do here. I'm going to go ahead and say, in this case, print line, and I'm going to say 1, but I'm going to yield the value of 1 right in here. So when I run this code, what does the output say? It said 1, and then it said in the loop 1. But then I can immediately say print line, I'll say 2, and I will say yield of 2, and then I will also go ahead and say one more time print, and I'll say 3, and I'm going to say yield of 3 one more time. So when I run this code, notice how I'm entering and exiting this function multiple times. And so, in other words, that is a coroutine right there. So a coroutine, the word routine is just a function, a subroutine. But a subroutine is where you enter the subroutine and then you exit the subroutine in the end. But a coroutine is where you have 2 routines, but they work together, they collaborate. So you enter here, you can enter here, you can enter here, and you can keep going back and forth, and you can execute as the timeline progresses. You can be executing chunks of code in each of those, and they can collaborate and work together. So this gives a way for us to really move across the progression of this. And this is a very powerful concept. But this concept is even more exciting because there is something even more fundamental behind coroutines. A lot of times when people talk about coroutines, they talk about how cool coroutines are. But to me, there's something even more cooler than coroutines, and that is really continuations. And continuations really is what makes this possible. And I'm going to say continuations is one of those features we've been waiting for a lot of time to be able to do in the JVM. And we can actually start using continuations in different languages, including Java moving forward. This is going to be a very prevalent idea moving, we're going to come to it. So we'll talk about that in just a few minutes even more. But what about threads? Well, talking about threads, I want to spend a minute on this just to understand how this actually works. So let's go ahead and say we have a task 1. And in the task 1, I'm going to simply, actually, let's do it this way. Let's go ahead and say this is do work, and the do work takes an integer. So what I want to do here is to simply say do work called with, and we will output the value n, and from, and we will output the value of thread. Let's go ahead and say thread dot current thread and display the thread information. If you look at this over here, this is going to simply say, you know, it was called, with what value it was called, and where it was called from. Just to understand this, let's go ahead and say run blocking over here, and I'm going to simply call do work with, let's say, a value of 1. This should be extremely simple to understand what's going to happen. As you would expect, the do work is going to be called, but it's going to be called from here. I'm going to pass a value of 1. You would expect do work called with 1 from thread. Should be the main thread after all. That's what we are expecting this to run the code. Let's see if that's actually true. And sure enough, you can see it said do work called with 1 from main thread. So that's no surprise there. However, I'm going to go here and say launch, and in this case, I'm going to call do work one more time, and the do work is going to be, let's say, thread number, value number 2. And then, of course, when I'm done with it, I'm going to simply say done in the very end. When I run this code, what is it going to really do for us? Notice that it is asynchronous as you would expect, but where did do work run from? It ran from main again, which is kind of understandable what just happened here. Well, the launch was called from within the main thread. It decided to just run it from the main thread. This is truly a coroutine. Remember what coroutine is? It's interleaving. I am munching with my mouth, but I'm also speaking on the phone, and I interleave between those two. That's what the main is doing. The main is interleaving between two pieces of work and saying, I'll do this a little bit, I'll do this a little bit, and I can go back and forth, and it's interleaving these two tasks. But you can also say, I don't need to be doing this. Sometimes you hand the phone to somebody else and say, here, you talk to this person, and I can go have my meal. So you can peacefully eat your food while the other person is talking on the phone. That's perfectly fine. And how do we do this? Well, you can then say, change a context of execution. So I'm going to say global scope dot launch. If you don't say global scope, the launch is inheriting the context from the current execution of the coroutine. In fact, you are already within a coroutine. When you launch within a coroutine, the coroutine inherits the context of the parent coroutine. Now you're saying, no, I don't want my parent coroutine. I want to be a complete separate child on my own. You're creating two different contexts at this point. So right now, as a result, when you execute this code, as you can see here, you can see that it starts off, but notice the second one is no longer in the main. It's in a completely different thread at this point. Now, just to add a little fun to this, let's go back to this code right here and say yield, and then I'm going to do a do work of 3, and then, of course, I'm going to call a do work of 4 right here just to see what it's going to do. When I run the code this time around, though, notice the difference in the way it executes it. 1 and 4 ran really quickly up there, not a big deal, but you can see the bottom ones were 1 and 1. But of course, this is the nature of demos. We cannot be really sure about it. Now, I don't want to change it yet because it's different and we can capture it. You can see the last are not the same at this point. It's 1 and 3. A minute ago, it was 1 and 1. Hey, the same thread decided to run it, but it's not really required. It could be any thread because I yielded it. Well, the reason for this is when I launched the global scope, there's a pool of threads available to it. One thread was executing the code. I called a yield, and that thread goes away. And when the yield is done, another thread comes and picks it up. This is kind of like you are in a restaurant. You're having a meal in a restaurant. You may be sitting in a particular table in a restaurant, and then you leave, and maybe you're done, and you come back the next day, maybe it's really a favorite restaurant, you like to eat again there, and then you come back, you could be sitting in a completely different table, for example. So if you think of a table as a thread that's executing it, you could be switching, even though you're the same person, you could be having different sessions. Or it could be an example of a waiter. A waiter may come and help you, may go away, but another waiter may come and serve you water or drinks. So it could be different people serving you, even though you're sitting there for maybe an hour for your meal. So the point really is you can have this context switching, and you can see that happening here. So in other words, what I want to emphasize here is, generally speaking, don't spend too much time thinking about threads when it comes to coroutines. You need to be aware of them a little bit, but the essential idea here is really interleaving task and being asynchronous, and that is the essence of it. And if you're saying, you know what, I want to be non-blocking, well, coroutines give you the non-blocking nature really readily, and that works nicely well. However, I want to really take a little bit of time and understand what's going on. How do coroutines actually work? What's really happening? For that purpose, I want you to, let's simplify this code a little bit and see how this is going to work. I want you to just look at this part right now. When you look at this code, how in the world can this code do the do work, and then it can do the yield, and then do the do work, but how did it really become asynchronous? How can it really switch between even threads of execution? What is the magic? Well, before we talk about that, let me just summarize what we talked about so far. And that is one of the most emphatic things I want to say here about coroutines. So this is present, and this is going to be, in the case of streams, do this. Now, what does coroutines do? The coroutines give us this beautiful opportunity. The structure of asynchronous code is the same as the structure of synchronous code, right? So this is one of the benefit you get, synchronous imperative style code. So this is one of the biggest benefits you get out of coroutines, is the structure of asynchronous code is the same as the structure of synchronous imperative style code when it comes to coroutine. So I always look for what is the major learning for me when I look at a certain idea or a technology, and to me that is the major learning for me. And that is the structure of code is exactly the same, whether you want to do sequential versus parallel, or you want to do synchronous versus asynchronous. And these technologies help us to stay sane, because we can write the code easily for sequential and synchronous execution. We can debug it better, understand it, it's easier to maintain, it's easier to test it, and then you say, great, now this code is working, I want to flip a switch, and I want to make it asynchronous. You don't have to turn the code into a monster. You just make a very small change. The structure is the same. You add a suspend, you add a yield, you keep the structure the same, and suddenly your code can be asynchronous rather than being synchronous, and that's a lot of power on our hand. You're able to change the behavior of the code without altering the structure of the code, and that is enormous power on our hands to be able to deal with the code in a nice way. So that's exactly what we saw here. But from the curiosity point of view, how in the world can this actually happen? What is really going on? For that, I want you to think about this a little bit different. So to understand that, I want to go back, because it's a little easier to explain it, I'll go back to this example we saw. So I'm going to say sequence right now. And remember this example we wrote, what did we do? We said print 1 over here, and then we said yield 1, and that's what we did. And then we also printed 2, and then we also yielded 2. But then we said for number in sequence, and then we simply printed out, let's say, the number. When we ran this, we saw how it went back and forth between them, but how in the world can that happen? So to understand this, I want you to just focus on this part of code for a minute, the highlighted part. Now, in the highlighted part, what's going to happen? When the code comes into this block of code, when the execution comes into this block of code, what it's going to do is the following. It says, hey, look, I'm going to return a 1 for this call. Typically, when you call a function, what happens? A function returns a value to you. But this one says, I am not just going to return this value to you, I am going to capture the rest of the code. And I'm going to capture the rest of the code into a function. And I'm going to return to you a tuple. The tuple is going to be the data that I'm returning and a function I'm going to return with it. You can use the data I return and call back into the function I gave you. So when you call back into the function, I can come in here and execute at this point that part. And when it hits this yield, what does it do? Returns a tuple again with the 2 and a little function. You can use the 2 and call the function again. But if I'm returning a function back to you, what kind of function can I return to you? Oh, I could return a lambda to you. What does a lambda do? A lambda is an anonymous function, and you can use the lambda to call the lambda anytime. But wait a minute, lambdas are awesome, no doubt about it, but there's something else I need in this example. Like what? It's quite possible that I might have some data that I created right in here. For example, what if I had a variable I wanted to define here called, let's say, factor equal to 2, and I'm going to return times factor. And then I'm going to say over here times factor. And I'm going to say over here times factor. Well, if I'm going to run this code, what is it going to do? It is going to return 2, 4, and 6. What's this magic? How can it, if I were true earlier, when this lambda is returned, how in the world can it know what the factor is? Because that's up here. Oh, wait, we know the answer for it. We know a special type of lambda that can carry the state with it. And we call them as closures. So a closure can hold the state, and so you can come back and call the closure, and it restores the state for you. Well, that's really awesome. But if you're going to be returning these lambdas or closures and working with them, gosh, that's going to make programming really hard, and that's going to be a lot of work. What do we smart people do when things become really hard? Well, in the real world, you delegate this. You give it to somebody and say, you do this, because I'm not going to be doing it. In programming, we call it abstraction. You raise the level of abstraction, and the abstraction says, I will do this for you so you don't have to worry about it. What is that abstraction we are talking about? Now you know the rest of the story. That abstraction is called continuations. So a continuation is an abstraction that takes a result of a computation and a closure, a part of code that's going to carry the state. And so when you get a continuation, you can consume the data, and you can fire back into execution, and that can in turn give you a continuation, and you can continue with this conversational state in this case. So this is like you and I maybe sit down and talk about something this evening, but tomorrow we run into each other at the breakfast. We can hit off the conversation where we left, isn't it? You don't have to reestablish our conversation. You don't have to reintroduce. Oh, you know what? I was thinking about what you said yesterday, and we know what we are talking about because we remember the context. That's kind of what continuations do. You can carry that over. Well, okay, that's a lot of talking. I want to see the continuations. Okay, I hear you. Let's go see the continuation. So notice what I'm going to do now. I'm going to go back to this command prompt. I'm going to go ahead and ask it to bring a file called sample.kt. So I'm going to create a class called sample. So I'm going to say class sample, and within the class sample, I'm going to create a function. I'll call it as first, and all that the first function does is simply return, let's say, 1. So all it is doing is it's returning a value 1. That's really a small, nice little function. But I'm going to say suspend over here function, and this is, I'll call it second over here. And what does the second function do? The second function simply says return 1 also. So when you look at this code, there is only one difference between these two functions, other than the name, of course, right? One is defined as a suspend function, the other one is not. But this is what we do at the code writing time. But the Kotlin compiler says, aha, you said suspend. What that means is you might call this function in an asynchronous context, which means I've got to yield to the caller at this point, and then you might come back and execute the remainder of the code later on. So I'm going to capture what's below it into a continuation and ship it. Well, let's see if that's actually true. So what am I going to do? I go to the command prompt. I say Kotlin C JVM, And I'm going to compile this using the Kotlin compiler, sample.kt. And all I did was I compiled it. Now you can see I have a sample.class on the disk. Now I say java p minus c because I want to examine the bytecode. On my machine, java p is an alias already with minus c. So I'm removing minus c because it's already on my machine. And I'm going to say sample and run that. Now when I look at the bytecode, what am I seeing at this point? Well, the first thing you see here is that's the first. Notice that's a very simple function. All it did was it took the constant and returned it as a I return. But second is very different, as you can see. What does second do? Second actually has a parameter, as you can see right in there. Notice in the source code, there was no parameter to the second at all. That's pretty darn empty parameter list. That's not the case when you look over here. All of a sudden, the compiler said, aha, you marked it as suspend, which means you want to resume this call context later on, and it wired this for you automatically. So it created a continuation for you, and it is returning, creating the constant, but it's returning back a continuation, which is going to hold the result and the rest of the code to execute for the context to come and resume. So all that happens behind the scenes by the continuation being implemented by the compiler. So the point I really want to emphasize is this. While we all can be excited about coroutines, and we should, my real excitement about coroutines really is it's backed by continuations. Continuations are the backbone of coroutines, and that is something we need to really keep in mind because this is going to become very prevalent as we move forward in our field. This is going to play a very big impact on how we're going to build applications to the large scale. So this is a very beautiful idea. Continuations have been around for a long time. Languages like Clue, decades ago, did continuation. We have not been exposed to these ideas in mainstream languages for a long time, but now we live in this beautiful time when the languages we program for our applications can also have these features, and so essentially almost all the languages will eventually start providing this. So a very compelling idea, as you can see. So that brings us to almost the end, and I want to do one more example here of something a little bit more practical, if you will. So let's do something a little different. What if I want to call into web services? And of course, I could sit here and create a complex web service. And then I can have more moving parts. And then we're going to spend more time struggling with my example than understanding how coroutines work. I'm fundamentally a lazy person. I don't want to do anything more than what I need to do to explain the idea. So for that reason, I found two services on the web I can use. One service is http stat.us. That simply returns a status code when you ask for it. Hey, that makes a remote call. That's awesome. Another one is the IP5, which is going to give me my IP address when I ask for it. So that's two services. But of course, you know what happens when you call services. Things could go wrong. Things could fail. So what do we do about handling this? Let's start with a synchronous solution first of all, and then we will make it asynchronous after that to see how that actually works. So let's start with the very first service to begin with. So what am I going to do here? Let's get rid of all this code we don't care about anymore. So I will get rid of the class that we created. I don't care about it. Let's also get rid of the sample.kt. I don't care about it. So the only thing left here is the sample. That's all I really want to have, nothing else. Okay, let's go to the sample.kts, again, the script. What I'm going to do now is I'm going to write a function. So the function I'm going to write here is called, get, let's say, response. So what does get response do? It takes the code as an input, and it's going to return a string for us. So java.net.url, and I'm going to return the response for that particular code from here. And I'm going to say .read text. So this is going to return to me whatever that particular URL is going to return to me. So that's pretty darn simple, as you can see. What's the next thing I'm going to do here? I'm going to write another function, get IP address. And what does the get IP address function do? Returns a string again. Keep it extremely simple. And I'm going to just copy this over for a minute. But I'm going to simply change this URL and the URL is going to be this URL that I have here, which is what I'm going to use for this purpose. So I got two little functions. The get response is going to return a response. The get IP is going to return the IP address. Now what do I want to do? Let's go ahead and say run blocking one more time. And in this case, what I'm going to do is I'm going to ask for the get response to execute. So what am I going to do for the get response to execute? So I'm going to say global scope.launch. Well, in this case, I'm going to launch a task. I'm going to say job equals, let's start with baby steps. I'm going to say job.join and wait for that to finish before I exit the main thread. Now I'm in this other thread. What am I going to do here? I'm going to say response is equal to get response, and I'm going to send a code to it. What in the world is the code? So let's go ahead and say code is equal to if mat.random is greater than 0.5, then the code is going to be 200, otherwise the code is going to be 404. So I can return a 200 or a 404 for this purpose. This reminds me of an experience. I can never forget this. There was a day at my home. This is when you know you've really made it as a programmer. I was sitting at my home. In the kitchen I was working when my son came to me and he had a question. And I really was too busy. I didn't want to answer him, but yet I wanted to give him an answer. So without saying anything, I'm not even kidding, all I told to him was 302. That's all I did. And without missing a beat, he turned around and said, Mom, and he went to my wife. And my wife, without missing a beat, said 404. And he's like, damn, and walks away. When the entire family can communicate in HTTP code, you know you've made it, right? So this is going to be return a 200 or return a 404. I'm going to return one of those code, and HTTP status simply returns back the code you sent to it. But I'm going to send a little delay of a sleep over here. That's going to take 2 seconds to simulate a network delay more than the network delay we will normally have. So this is going to be the response from this. But you know the problem here. If I were to print out, if I say the response is, and I'm going to print the response, you know this won't work. Why wouldn't this work? The reason this won't work is, you know that in this particular case, it's not going to get a response all the time. There are times when this is going to quite fail miserably because the code may be 404. In that case, we're going to get an exception from this code. So just to entertain this thought, what's going to happen here, if I were to go back and run this code, it is going to fail with an exception, if you will. So let's go ahead and run the code and see what it says. So the response is, and if it went really well, it's going to be 200. If it didn't go, oh, there you go, 200, okay. This is when the response was good. But what if I run this again? And what if the response is not going to be 200? What's going to happen at this point? And you can see it blew up right there. Gosh, exception, what do we do about the exception? Here's an idea. Why don't we try this? Try, and we will put this response right in there. We will go ahead and put this in there as well. But then we'll say catch exception. And in this case, of course, very politely, we will print the exception right in here. So you know what's going to happen now. We made a call to the service. If it were to fail, you want to handle the exception and print the exception. So sounds reasonable, isn't it? So let's take a look at what it's going to do at this point. We can get the output being displayed after the call is made, and so we can take a look at the output at that particular point. Let me just run this and see what it's going to do right here. So if there was an exception, it's going to tell us there was an exception. If there's no exception, it's going to tell us the response is and print the status for us. Well, that worked really well. This is a sequential code as we all know it. So what am I going to do now? I'm going to then say val IP is equal to get IP address. And of course, that may run into trouble also, we know, because you may have a network problem, you may have an error. What are you going to do about it? I could put a try block again, and in this case, I'm going to wrap that right there. And if it was an exception, I'll say exception. This is going to be an exception, and I will go ahead and print out the exception at that point if something were to go wrong. But then, what do I want to do? Now that I've done this code, I can go back here and say the response for request from, and I can say IP is, and I can print the response. So if everything went fine, I'm going to see the response from the request from IP address is response. If it were to go wrong one or the other, we're going to get an exception and we're going to display it. Seems really reasonable. But this is a sequential code. It's going to do one and do the other. Is it true? Let's go ahead and put a little print. We'll say, in this case, a little request that says get response. And then I will go here, over here, and say get IP address. So you will notice that it's going to print the first one, and then it's going to wait for the response to come back. It's going to print the second one. That's what we expect this to do. Let's actually see if that is actually true by running this code so we can actually enjoy the output. So when I run this, it says get response. You can see it's waiting right there. Then it says get IP, and then it said 200. If I run this again this time, though, it's waiting for the response to come back, and then it asks for the IP address after that if it was successful and displays the result. Of course, I want this to fail this time, and it usually doesn't when you want it to. I'll try one more time, otherwise we'll move on. So you can see in this case it's getting the response, but if it were to fail, there you go, it failed. But how much time is it going to take to do this? So if I run this code with the time, you will notice that in this case, it's going to take some time to do this work. You can clearly see we are waiting. And then when the response comes back, we make the next request, and then we move forward right after that, if it was successful, that is. And then you can, gosh, it's taking a little longer, as you can see. But anyway, you get the point. Whatever time it takes for the network to come back. Hello? OK, it looks like it's gone. So let's try this one more time. All right. But how do I make this asynchronous? Before we make it asynchronous, let's talk about some challenges, first of all, that we may have to deal with. So about 7 seconds, as you can see. Going back to this, if I were to make this asynchronous, there are some really important issues to deal with. I will make this asynchronous. The problem is, I can make this asynchronous. Now, I got 2 requests running. What if the first one fails? What if the second one fails? What if something else fails within the coroutine? And this is one of the things about coroutines. The coroutines are managed by the parent. If one of the child coroutines blows up, it will kill all the other coroutines as well. So they will send a cancel message and say, hey, look, I am running here, you are running there, we don't know each other, but I failed. I tell the parent I failed. The parent will tell the child, this is of no use because one of the other child failed, you quit as well. So that is the beauty of abstraction, isn't it? The abstraction is managed by this for you, so you don't have to do the work. So how do we make this asynchronous? Let's give it a try. So first of all, I go to this code, and I'm going to say async. So remember we used launch a few minutes ago, if you recollect. We said launch. What's the difference between launch and async? First of all, launch and async do the same thing. They will run this coroutine as an asynchronous process. So launch is asynchronous as much as async is asynchronous. The difference is launch is an action. You say, do this and go away, fire and forget. I don't want anything back from you. Async, on the other hand, returns a deferred object. So if you look at the type of the object, it's a deferred object. Think of it as a future if you want to. So you get back a deferred object from a call to async. You don't get a deferred object from a launch. What does launch return to you? Launch returns a job. Well, async returns a deferred object, which is going to implement the job interface, but can also give you back a data. So in this case, I did an async and called the get response. And similarly, I call async here and call get IP address. But at this point, this will fire away, not be blocked, and this will fire away and not be blocked. When both of them finish, if both of them finish successfully, then I can say await, and I can get the data from the deferred object, from the response, and from the IP as well, and I can call the await to get it from both of them. So as you can see in this example, what is it going to do? When I run the code, I want you to notice how it actually displays both of them right away. Earlier, you remember, it was waiting on the first one to finish before it started the second one. In this case, it fired up both of them. So both the requests are now running asynchronously, and when both of them finish, we'll get the response, And of course, at that point, we can move forward. We don't have to wait for one to finish to start the other. As you can see, the network connection here is pretty bad, so that's one of the reasons why you're seeing this becoming really slow, but you get the point. So the idea really here is, without the async, if I roll back the change I made a minute ago, just to illustrate the point again, if I were to roll that back over here, this is purely a synchronous call at this point. So right about now, so you can see that's pretty much a synchronous call. And when I run the code, you can see it makes one call, and it is waiting for it to finish before making the other call. On the other hand, though, if I were to go back here and make them both asynchronous, what's going to happen now, it's going to fire the first one, fire the second one, and then await for the response from both. So as a result, if I go back to this code and run this time, you can see it fires up both of them right away, and then it's waiting for both of them to finish, and they're running asynchronously at this point, if you will. So hopefully that gives you an idea about how we are able to turn this code into an asynchronous computation. Don't bother the time here because the network delay is pretty unpredictable here, but it gives you the point. So you can see how it is very easy. So just curiosity's sake, what is really IP that you are getting at? Well, let's go ahead and say output for a minute. I say IP dot what. So that way we can really look at the error and understand what the type is very easily. So if you look at this, it doesn't know what a what is. Let's actually do this way. Let's go ahead and say val something, a string is equal to IP, just to prompt this to give us an error about type mismatch, and we should be able to see, there you go. So the type is a deferred, and then a type T, whatever the type is, it's a string. And so that is basically what is being returned by the async. So that deferred object, you can go ahead and call the await on it and extract the data when you want the data eventually. So that gives you an idea. But notice one big difference though. When you look at this code, this is pretty much a imperative style code we are all used to. Now what is really powerful here, the powerful nature here is you can call a function, you can handle its exception, you can have multiple nested levels of exception. And we are used to this in our programming, where you call a function and then you call another function, but you have to deal with and recover from exceptions on multiple levels. You may say, if this fails, do something else. Maybe I talk to one service. If that fails, I'll go to an alternative service and deal with it. Doing this in functional style is incredibly difficult because you're saying, I'm going to make this call to this service. If that were to fail, I go to this other service. How do you really program this in functional style? It is almost trivial to do this in imperative style, really hard in functional style, because that's not the capability of the functional style of programming, whereas you are able to take this imperative code, but you're able to preserve the structure of the imperative code and yet make it asynchronous by simply adding this little annotation for making it asynchronous. And that's exactly what you saw here, is that you're able to get the result in a deferred mode and execute it. So that gives you an idea about how we're able to take this code and turn it into asynchronous execution without much effort at all. So to summarize what we talked about, what we are doing here is much like how Java 8 streams made the structure of the parallel code the same as the structure of sequential code, coroutines make the structure of asynchronous code the same as the structure of synchronous imperative style code. And as a result, you can write the code synchronously, reason it, debug it, test it, and then when you want performance and where you need it, you make a slight change and you're able to branch off to coroutines. And this is something that Kotlin provides pretty nicely, but not only can we enjoy that today, but this is the direction in which we're going to go in Java as well in the future. So the sooner we get really comfortable with it, not only can we benefit now, but we can also enjoy this quite a bit in the long run as well. And that is something we can benefit greatly moving forward. So that's basically an example of how coroutines work in Kotlin and how we can benefit from it. And of course, there's a lot more depth to this than what we talked about here, but hopefully that gives you an idea. If you're interested in downloading the code examples, you can go to the URL here, and you can download it from the downloads link. Hope that was useful. Thank you.